Hello, my name is Sekiyama, Division of Materials Physics, Graduate School of Engineering Science, Osaka University, Japan. In this movie, I would like to show the basics of many-electron systems assumed for those in atoms or ions, where the consideration of Coulomb and exchange interaction between electrons are important. After the introduction of the Slater determinant, Coulomb and exchange integrals in atoms, I explain the concept of the second quantization. Please enjoy this movie.
In this lecture, I start from Hamiltonian of electron in a crystalline solid. There are so many electrons in solid. Here the large N is of the order of 10 to 23rd. There are so many. Of course, each electron has a kinetic energy and bound in some potential. This is the potential from nuclei in the unit cell. And we need to sum over the crystal for the potential. Furthermore, we need to consider the Coulomb interaction between electrons. These two terms are categorized in the one-electron Hamiltonian. Therefore, we can rewrite the total Hamiltonian like this one. So the first terms stand for the kinetic energy of electron and potential, and second term stand for the Coulomb interaction. Here it should be noted that I use the Gaussian CGS unit. Of course, the direct calculation of this Hamiltonian is not practical at all, even if the second term, this Coulomb interaction, is neglected. In the case of the solid-state spectroscopy as well as the condensed matter physics, we use translational symmetry of the crystalline solid. Then the valence band electronic structure can be solved. Inner core electronic states are to some extent similar to those of single atom or ion. But even in the single site, there are many electrons of the order of Z, large Z. Large Z means atomic number. So there are many electrons occupied even in the one site where the effect of the Coulomb interaction represented by the E square over Rij are not negligible at all. Therefore, I start to explain how the electronic structure is affected by the Coulomb interaction on the single site. Before going to the Coulomb interaction, I explained one electron wave function of the hydrogen-like atom. So this is a Hamiltonian for an electron in the hydrogen-like atom. Here, implicitly, I use an adiabatic assumption for which the nucleus is fixed on the origin of the coordinate. Then the small r stands for the distance between the nucleus and electron and representing the electron position. When there is only one electron, we can solve this Hamiltonian and obtain the eigenwave function, which determines the atomic orbitals like this one. Here we use polar coordinate, three-dimensional polar coordinate, and then the wave function are expressed by the product of the radial function as a function of small r and spherical harmonics as a function of the polar angle theta and azimuthal angle phi. After the calculation, we obtain the quantum numbers NLM. N is a principal quantum number, L stands for the orbital quantum number, and M stands for the magnetic quantum number. And further, we need to take the spin of electron into account. This one is rigorously obtained from the Dirac equation, relativistic quantum mechanics, but here I simply introduce spin wave function alpha and beta. Alpha for the upspin, Sz of plus 1/2, and wave function beta for the downspin, Sz of minus 1/2. So this zeta stands for the spin coordinate, taking only two values, plus minus 1/2. Then the spin wave function has this nature, so also normal nature, like this one. Then the one electron wave function with a joint index, lambda. Lambda is a joint index of n, l, and s. We can represent one electron wave function as a product of the eigenfunction psi and spin wave function sigma. Sigma is alpha or beta. Then I introduce four-dimensional coordinate x, r, and z. So by using this wave function, we can express many electron state in ions. So this is a Hamiltonian atom with atomic number Z. So first two terms stand for the one electron term, kinetic energy and potential from nucleus. And this term stands for the electron-electron Coulomb interaction. At first, we consider the case of the electron-electron Coulomb interaction as switched off, and there are Z electrons in atoms. In such a case, we need to consider the wave function of the state with the number of electrons of Z. The first easy way to take the wave function of the many-body electron system as like this one. So simple product of each eigenstate. However, it should be noted that the state is physically equivalent after the exchange of electrons, which is not taken account in this formula. So since the electrons are fermions, the many-electron wave function must be antisymmetric with respect to the exchange, as like this one. So this wave function is expressed after the exchange of the electron 1 and electron 2. Such wave function is minus of the original wave function. So this formulation does not satisfy this condition. Therefore, we cannot take this wave function. Instead, we use the Slater determinant expressed as this determinant. This determinant satisfies this antisymmetric nature of the fermion many-body wave function. Therefore, we need to consider the wave function as this one. Then we consider the situation of the many-electron. So this is the simplest one. The number of electrons is 2, namely helium atom. When we consider the electrons as fermions, we can imagine that the ground state configuration as the electron is occupied in the lowest energy levels given by the 1s orbital, where the spin degeneracy is 2. Therefore, the lowest ground state electron configuration is 1s2. Then we consider total energy of this configuration. According to the definition of the Slater determinant, the wave function of 2 electrons is given by this formula. After we consider this many-body wave function, we can obtain the ground state energy of this state according to the rule of the quantum mechanics like this. So this is a Hamiltonian. We put here and we put this wave function here. Then after the calculation, we get the energy, ground state energy, with 2 electrons in helium atom. So this is a calculation. So the formula becomes so long due to the presence of the spin wave function. And we see the effect of the spin wave function. We can understand that this term gives a finite value as 2. On the other hand, due to the presence of the product of this one and this one and this one and this one, these terms give 0. Therefore, the total energy can be divided into this part and this part. So this one represents a Coulomb integral. And first term stands for the 1 electron energy made of the kinetic energy and potential from nucleus. Then we get the total energy like this. So this U means a Coulomb integral between the 1s electrons. In this way, I introduce a Coulomb interaction, Coulomb integral. But to fully understand the electron-electron interaction, another term is required. I introduce exchange interaction by using the lithium atom. So the number of electrons of the lithium atom is 3. Then we consider the ground state configuration. This is 1s2 and 2s1, where the 2 electrons with opposite spin direction occupy the 1s orbital, and the second lowest energy level is for the 2s orbital. Therefore, the 1 electron with up spin occupy this level. Let us consider this configuration. Then the total wave function is expressed by the 3 times 3 Slater determinant, expressed like this. Then we can calculate the ground state energy for lithium atoms. Then we start. So the formula becomes so long because we need to consider the few different Coulomb interaction. So first 2 terms stand for the 1 electron energy given by the kinetic energy and potential from nucleus. So this is for the 2s orbital electrons. Then we need to consider the 1s Coulomb integral between this one. The second term stands for the 1s Coulomb integral, like this one. So since there are 2 1s electrons, these 2 must be multiplied. And after the calculation, we can notice this term is given. This is due to the nature of the Slater determinant. This is similar form to the Coulomb integral, but the coordinate is exchanged between the conjugate part and the original part, like this. For instance, here the R1 is put in the 1s orbital wave function, but for the conjugate, R1 is in coordinate of the 2s orbital. Of course, R3 coordinate is for the 2s orbital in the original state, and for the conjugate state, R3 is in the 1s orbital wave function. This is obtained by the calculation of the spin wave function. This term is not given by the classical framework. This integral is first given by using the Slater determinant. This Slater determinant is obtained from the condition where the many-body fermion wave function must be antisymmetric after the exchange of particles. So therefore, this term is characteristic of the quantum mechanics. This is called as exchange integral. here the concrete exchange means exchange between the 1s orbital and 2s orbital with the same spin. This integral gives a finite value for the combination of the same spin electrons, like this. Okay? Then we get total energy like this. It is known that the exchange integral is positive but smaller than the Coulomb integral with the same combination 1s and 2s orbitals, like this one. So then we notice that the 3-electron energy is expressed by using this formula. The first two terms represent 1-electron energy, and this term gives Coulomb interaction between the 1s orbitals with different spin alignment, and this term gives 1s 2s Coulomb interaction, and final term gives the exchange interaction between this one. This exchange interaction gives an important role in the quantum mechanics. Then I expanded this concept to Coulomb and exchange integral in the general z-electron system. For the z-electron system, we can describe the wave function like this one using the Slater determinant. Then now we can calculate the total energy of this state like this one. So this is 1-electron energy from the kinetic energy and the potential from nucleus. The number of term is Z, large Z, and the second term stands for the Coulomb interaction between the electrons, where the number of the term is like this one, and third term stands for the exchange integral, so the combination of the state lambda I and lambda J with the same spin direction, this one or this one. Therefore, we need to divide the number of electrons n alpha and n beta. N alpha means the number of upspin electrons, and n beta stands for the number of downspin electrons. Of course, sum of L alpha and n beta is Z, like this. Therefore, the number of term is expressed by using this formula. So the situation is like this one. All vertical line with arrows stand for the occupied electron. Arrow indicates the direction of spin, up spin or down spin. Then we consider this situation, whether we can define the 1-electron energy of the state lambda L, this one red one, or not, in this z-electron system. Now we assume that we can define the 1-electron energy of this state as this formula. So the first term stands for the 1-electron energy from the kinetic energy and potential, and second term stands for the Coulomb interaction between this electron and the other electrons. Therefore, the number of the term is z-1, and the third term stands for the exchange integral acting only for the same spin electron. Here we suppose the state lambda L is for the upspin state, and thus the number of term is n alpha minus 1. Then we consider the z-1 electron energy without this state. We can consider total energy of z-1 electron as this formula. So this is 1 electron energy of the residual z-1 electrons, and second term stands for the Coulomb interaction between the electron without the electron with the state lambda L, and third term stands for the exchange integral between the electron without state lambda L. Then we consider the sum of this assumed 1 electron energy and residual z-1 electron energy. when we compare the formula, this formula, we can notice that sum of this energy and this energy is equal to this energy. That means that we can define the one electron energy with this state is energy difference between the original total energy and residual 3-1 electron energy, like this one. By using this way, we can also define the one electron energy state even in the presence of the electron-electron Coulomb interaction. In such a case, the Koopmans theorem, which is introduced in the last lecture, where I assume that the electron-electron interactions are switched off, but this is equivalent to the Koopmans theorem because this is the electron total energy and this is residual z-1 electron energy, and this is defined one electron energy levels to be excited. So that was Koopmans theorem. Therefore, this consideration is equivalent to the Koopmans theorem. That means Koopmans theorem is still satisfied for the Slater determinant, namely when we consider the many-electron state by using the single Slater determinant, we can define the one electron energy level for the state lambda L, like this one. But one important thing is that simple sum of each one electron energy is no longer becomes total energy. When we simply calculate the sum of the one electron energy defined as this formula, Coulomb interaction are so-called double counted, so overestimated. Therefore, when the Coulomb interaction is switched on, we cannot obtain the total energy by the simple sum of the one electron energy levels. Next challenge is to obtain how this wave function. The problem is how to solve each one electron wave function from the given condition. So, in order to obtain this Slater determinant, we need to obtain the one electron wave function with also normal condition expressed as this formula. And we need to get the minimum energy for the given Hamiltonian. According to the Hartree-Fock approximation, to satisfy the condition of the minimum energy and also normal condition, the Hartree-Fock equation for electrons are obtained like this. So this is rather complicated. This term stands for the one electron Hamiltonian, and second term stands for the Coulomb interaction, and third term stands for the exchange interaction. This line is for the phi lambda I, state lambda I, coordinate of the x1, and right side of this formula, the energy of the state lambda I electron like this, and the function as this one. But this term, wave function for the other state lambda j, and lambda I is in this integral. Therefore, this Hartree-Fock equation are so complicated, but usually the solution are obtained by the numerical calculation. So now we assume that by using this Hartree-Fock approximation, we obtain the information of the wave function of each state lambda I. Then we can express the total Z electron state by using the Slater determinant. So this is the story of the first step of how the many-electron system should be described. The first step is to use this Slater determinant. From now, I change the topic, the second quantization of electron. So far, I have explained the Slater determinant for the electron system. There is one problem to use the Slater determinant directly, because the Slater determinant depends on the number of electrons. That means when the number of electrons is changed, the Slater determinant also changed. That is rather inconvenient. One of the convenient ways to describe the many-electron system is that we use the occupation number. This is an eigenstate because these states are mutually orthonormal. So such all one-electron wave function have been prepared in advance. Then we set the electronic state by using the occupation number. So this is the idea of the second quantization. So by using this idea, empty state with there is no electron equivalent to the vacuum state as this formula. Then the electron state, this is equivalent to this Slater determinant as this formula. So the electron occupies up to the lambda z state from the lambda 1 state, like this one. In order to describe this state from the vacuum state, I introduce the creation operator of electron as a lambda I dagger, as this one. Then the state phi is created by using the creation operator from the vacuum state, like this one. So this is equivalent to the formulation of this. Then we can also consider its conjugate, the annihilation operator of the electron, as a lambda I. So the vacuum state can be expressed by using the state phi and annihilation operator A, like this one. Okay. In the second quantization, a dagger and A is introduced. Then I explained the property of the creation and annihilation operator by comparing these two states. For the creation operator, when we create or when we occupy the electron into the state lambda I from the vacuum state, we can describe such a state as this formula. But when we put the additional electron into the lambda I state, which has already been occupied in the state phi, we cannot put in the same state. The state becomes zero. I forget to say the nature of the Slater determinant. If we put the same one electron wave function into the Slater determinant, by the calculation we understand that such a state is cancelled out and becomes zero. On the other hand, when we consider the one electron is additionally put in the empty state, that is possible. Such a situation is described by this formula, and in this case, we need to consider the factor of -1. One electron is created in the state, empty state, lambda z plus 1. So in order to reach this state for this creation operator, we go through the 1, 2, 3, 4, 5, I, and z times. Therefore, we define this state is not simply this one, but multiplied by this factor. For the annihilation operators, for the empty state, the state becomes 0, since there is no electron in the lambda I state. For the occupied state, annihilation of electron is possible when we consider that we removed one electron with the state lambda I by using the annihilation operators. So in order to reach this state, electron goes through the other electron by I minus 1 times. Therefore, we need to multiply this factor. By using this rule, we consider this procedure, namely for the state phi with a number of electrons of z, once electron is removed from the state lambda I and put again for this state. So by definition of this one, we can calculate this state. Then we need to consider this state to be switched to 1 by saying this one. So the number of the electron in this state is I minus 1. Therefore, this term is again multiplied. Then we get this is equivalent to the original state phi. We consider its conjugate procedure like this one, but we can easily understand that this state is 0. This state becomes also 0. Therefore, summation of this procedure and this procedure becomes 1. This is usually known as an anti-commutation relation, expressed as this formula. Then we consider another rule. This is for the occupied state. Then we consider the operation for the unoccupied state. So now we consider this state, the one electron from state phi, the additional electron is going into the empty state, lambda z plus 1. Then we get this result. And then we removed this state. Then in order to reach this state for this annihilation operator, we need to travel the z times for the occupied electron, and therefore we get this formula, and finally we get this result. We consider its conjugate operation like this one, but for this state is empty in the initial state phi. Therefore, when we operate the annihilation for the empty state, the result becomes 0. Therefore, this conjugate operation gives a value of 0. Therefore, we get this relation irrespective of the occupied state or unoccupied state. So this term gives the occupation number of electron, because if we operate this combination operator for the empty state lambda z plus 1, the result gives a 0. But for the occupied state, this operation gives 1. Therefore, we can define the number operator of an electron as this definition. So the number is 0 or 1. For the empty state, this operation gives a number of holes. When we apply this operation for the occupied state, the result gives a 0. Since for all the occupied state there are electrons, therefore the sum of these two terms becomes 1. Every state is occupied or unoccupied. So now we consider another operation, like this one. Here state I and j is less than large G. That means state lambda I and state lambda j is occupied. Then we consider this situation, this operation. So at first we remove the electron with a state lambda j. Then we get this result. And then we remove the electron with a state lambda I. And we get this result. And we consider the different operation with exchanging the order. In such a case, the result is like this one, and after that, since the number j is larger than I, therefore factor becomes different as j minus 2. Therefore, this operation gives this result. So when we change the order of the annihilation, the sign becomes different. Therefore, the sum of this operator and this operator becomes 0. This is the same for the creation operator. Therefore, this relation must be satisfied. So compare with this one and this one. Finally, we get this relation. This is an anti-computation relation. Then, by using the second quantization, we consider the Hamiltonian of the many-body electron by using the second quantization. I talk about how the electron Hamiltonian is expressed by using the second quantization. So this is the original many-body Hamiltonian for the number of the electron of Z. In this case, we can calculate the total electron energy as this formula, which has been explained in the previous slide. This first term stands for the one-electron energy, and we can define as epsilon lambda I0. That 0 means bare electron energy. It should be noted that this energy is less than 0 minus because electron is bound to nucleus. The Coulomb interaction is obtained by this calculation, and we can define Coulomb energy as this one. So lambda, a combination of the lambda I and lambda j. By the same manner, we can also introduce amount of the exchange energy. Here we need to pay attention that the combination is electron with the same spin direction. Then we can express Hamiltonian as this formula. So important thing is that this should be infinity. Instead, we set occupation number operator here and here, like this one. Then, when we remind that the occupation number is defined as this formula, by using the annihilation and creation operator, this one is same as this one, and if we change the order, in order to keep the sign, that this operator should go through the even times, then this one is equivalent to this one. Then we can also express electron Hamiltonian by using the second quantization and annihilation and creation operators like this one. The next problem is how the photoexcitation process is expressed by using the second quantization.